Hello, everyone. So today I'm going to talk about building distributed queues using FoundationDB in Tigress. So, but before that, who I am, I'm Himank, and I am CTO and co-founder at Tigress Data. I'm CTO and co-founder here at Tigress Data, which is a global object store. And prior to starting Tigress, I was tech leading a dog store project at Uber, which is a real-time transactional global database and which was powering Uber's all real-time transactional use case. And being in the storage platform, being doing this for some time, we wanted to give that seamless experience outside of Uber as well. And that's how we started Tigress. For this talk, I'm hoping that I'll shed some light on the operations at Tigress and how we are doing that at scale. Then I'll also talk about what and how's of FoundationDB and how we are leveraging FoundationDB to build our queuing system at Tigress. And then lastly, I'm hoping to share some reusable patterns that you can apply for your use cases as well, even though you may not directly needing queuing system, but it may help the architecture that I present, that may help you, that may guide you with some other similar use cases as well. Now, before I jump into why we build queuing system or how we build queuing system, first thing is what is Tigress? So Tigress is a global object store which is S3 compatible, and the since day one we are global, which means we are in multiple regions, and we are in 11 regions right now. And the one of the core architecture design that we have chosen is that the data store close to the users. So what that means is, so for example, if you use Tigress, you'll just get a single bucket and you can write or read from anywhere across the globe. For example, if you write from Washington and if you read from Washington, your data will live in Washington. But if you read, for example, in Sydney, or if you read from Asia, anywhere, then we are responsible for automatically moving the data close to you so that your latencies are low. And then your user experience is still, when they access data from your bucket, they will still get low latency read. So that's the high level idea. But doing that, we need to have some sort of coordination between these regions. We need to work around, or we need to build something so that we can move data around these regions, or we can figure out the metadata of the user object so that we know how to serve reads or writes for our users. And to extend that thought in this slide, so when we started designing this, these were some of the high level things that we wanted in our architecture or to support our architecture. We needed some way to replicate data across our clusters. And this data could be the user's metadata. When I say metadata, our user right is divided into metadata and content. So we have metadata of the objects, which has the awareness about where actually the content exists in this whole globe. So we needed something that can replicate the metadata across these regions because we need to make sure these regions are aware of the user data. We also have inbuilt caching in our architecture, which means that we cannot serve stale data to the user because user can still write in any region. And if we are caching the data in some other region, and when they write to some other region, we need to make sure we automatically invalidate these caches as well so that we can serve consistent read to the user. So we needed something that can also responsible for invalidating these caches. Then we also needed something that can move the content across these regions dynamically, either based on some access or some pattern or cache them for a short period of time. Then there are a few other use cases that are not drawn here, but we also have change event notification for the bucket. So when any write happens in the bucket, then we can also notify you based on the write to that bucket. So we needed something for that as well. So overall, we needed some framework that is responsible for all these asynchronous task management. Now we talked about metadata, we talked about these metadata clusters, but what are these metadata clusters? So this is our FoundationDB clusters. We use FoundationDB to store our core metadata. And there are multiple FoundationDB clusters deployed. But what is FoundationDB? So FoundationDB is highly available distributed transactional database. And the beauty about FoundationDB is that it provides very low level functionality that you need from distributed databases. It doesn't provide you it doesn't provide you any query layer. It doesn't provide you any indexes or schema or table, but it provides you very low level things that you need from a distributed database. It provides you sharding, it provides you replication, it provides you transaction, and transactions are also distributed. But then you can just interpret it as a raw KV store. It just provides you raw key and values. And it is used by Apple and Snowflake as well to manage their metadata infrastructure. So it was no brainer for us to use FoundationDB. It was between FoundationDB versus building something our own for storing the metadata. But we also don't want to reinvent the wheel by writing again the consistency layer or the transaction layer. So that's why we choose FoundationDB for our core metadata storage. Now, jumping back to the queuing system. When we started building this queuing system, we had some design goals in mind, and few of them are highlighted here. So the first one is, for example, atomicity. We wanted atomicity, and the reason for the atomicity here is we don't want to lose any event, because if we lose any event, that means that data won't be replicated, or we won't be able to notify or invalidate any caches. So that was very important for us. Similarly, scalability. So as we grow, we also wanted that this system, which is responsible for managing our task, will scale with our growth as well. Then fairness mainly because we will be having different type of task. So we wanted to make sure that one task type is not impacting other task type, and they are fair to each other in terms of the consumption of resources. At least once is fine for us because we have idempotency built in our task type. So we were okay with if the task got repeated and apply again. Sharding again, same thing with the scalability as well, so that we can able to shard these asynchronous task framework or queues. And then operational simplicity. It was important because we are small, so we also wanted to be simple in terms of operation. We also don't want to manage yet another system just for this queuing. So what did we build? So we built a queuing system for managing all these asynchronous tasks. And this is backed by FoundationDB for persistence. And this is inspired by Apple's quick paper, which talks about this. And they also mention that Apple also used this algorithm or architecture for their asynchronous task management as well. So what is happening here is the big box is our serving layer. So when a user request comes in, at that point, everything that goes in the metadata cluster happens in the context of a transaction. So when we process this request, and if we identify this is the right request, what we do is we process this right, we extract out the metadata that we need to persist. But at that point, we also collect all the events that we need to trigger corresponding to that task and buffer all these events in that transactional context. And during commit, we write it to FoundationDB along with the metadata for that particular object. So what we are doing basically here is in the transaction itself, we are committing the metadata of the object, but we are also enqueuing all the events that we need in our queue. Then on the right, we have this asynchronous deployments or the worker deployment. These deployment are also separated with different priorities, but let's say there is a deployment. We are referring here deployment A, in which there are multiple computes. And then these compute have multiple scheduler. One scheduler maps to one shard. So this scheduler is responsible for a particular shard in the queue. And then this scheduler, when it gets the item from the queue, it put it in the channel. Each compute also has multiple workers, and these workers are actually responsible for executing these tasks. And same applies to all the compute that will be part of this deployment. They are responsible for handling different shards in this particular deployment. And what we have done is we have priority based deployment. So we have a set of tasks that is responsible for a particular deployment and different set of tasks for different deployment. Now we talk about this high level view, but let's talk about a little bit on the work distribution. So this queue itself is sharded, and these colors are representing different shards in the queue. So when we are writing in the queue, then itself we are writing in a way that they are logically sharded. And this way, this work is already sharded in the queue. It's present in the sharded form. And then when this scheduler just need to know that which shard it needs to read from the queue. So it's reading basically a particular shard from the queue. And the way it is done right now is one scheduler can read one shard, or it can read one or more shards as well. But right now our configuration is one scheduler maps to one shard. Now moving on to shards assignment. So we talked about like work distribution, there are shards, and then we need to map these queue items to these shards. But how does these schedulers are assigned to these compute? So what we are doing here is we are running a gossip protocol among these compute deployments. And this gossip protocol is taking care of distributing these shards to different compute. And this tells the compute that whether you are responsible for this particular shard or not. And we also automatically scale up and down these compute based on the load. So this gossip protocol comes into handy because then we don't need to do anything. When we, for example, when we scale it down, and let's say there is just one compute in the deployment, then it will be responsible for all the 5 shards. And if we scale it, and in this case, let's say we add 2 more compute, automatically 2 more computes are added based on the load. Then each compute will only be doing one shard or only be responsible for reading one shard or processing one shard from the queue. So this is how shards assignment is done for us. Now moving on to, so we talked about work distribution, we talked about shard assignment, but how does an individual item get processed? So there is a concept of vesting time. So vesting time decides when the item is visible to be processed. So this is the way we can have the item itself in the queue but not get processed. And this is needed because what can happen is that you can read the item from the queue, delete it from the queue, but the worker can be down, and then you will lose the item. So what we do is we read, we take the lease, and then we bump up the vesting time, and then we put it back again in the queue. And then we give this item to the worker, and then the worker can process this item and keep renewing the lease. And once the worker is done processing the item, then worker can go and delete the item from the queue. This wall clock time basically here is showing that anything less than or equal to wall time is visible to all these schedulers to get read from the queue and to be ready to be processed. Anything beyond this wall clock time or in future, the scheduler doesn't see it. So there is no awareness about all these items. It can definitely happen that the worker still dies and the item is there in the future. For that, what will happen is when the time comes and the item is visible again, then that item is picked up, cross verified, and then only it is processed. That then it's assumed that some worker is died, so someone else need to take responsibility for this particular item. Now, based on this, if we recap our existing goals that we started for this queuing system, so now how did we tackle it with our design? So atomicity. So the atomicity we are getting because of the transactions. So when we write to the queue, we write it in the transaction. So we make sure all the events are there in the queue. We don't lose any events at that point. Also, when we process them, then also we add it in the queue back again, and we take the lease, and it's only removed from the queue when actually worker successfully executed the task, then only it will kick them out or delete them from the queue. Scalability, it's deployed on compute. So each compute is responsible for some set of shards. So that means it can scale by adding more and more computes. Shards are also logical. We can also increase the number of shards that we need. Fairness. So we have multiple deployments based on priorities. So we have deployments like high priority deployment, low priority deployments. And this is based on the task type as well. So for example, there are certain deployments with low priority that are responsible for some garbage cleanup. But then there are high priority deployments as well. For example, replication, which needs to happen with a certain SLA. At least once we have idempotency on the task type, when they apply the task, then we make sure that it's not, if it is applied again, then we simply skip the task. Sharding, it's multi-level actually. So one is we have queue, which is logically sharded. And then what we have done is we have all these tasks, different tasks that are grouped into task type. And these task type map to different deployment. So we have different deployments for different task type, which we can scale as well, different deployments. And then we have queue that is also sharded. And operational simplicity. So the operational simplicity is provided because we are using just single database, both for storing metadata as well as this persistent queue. If not for FoundationDB, then probably needed to use something else like Kafka or some message queue, but that would be like an additional overhead. We wanted the same database to just use it, and it worked out nicely because FoundationDB provides transactions as well, where you can use these patterns. So recapping on this, so we are using, so any async task processing a need can be fulfilled by this architecture. For example, replicating between clusters, notifying caches to different deployments, different clusters, or sending change event to your consumers, batch processing anything, garbage cleanup, deletion, anything can be solved by having this type of architecture. And we actually use it for all our asynchronous task processing. We simply define a task type, we just add it in our deployments, and then it will start storing those types and start executing it. Simplified operation for us, it's simplified because we are using same database, but it could be modeled with different databases as well, because all we needed is some way to transactionally commit and store it in the same transaction. Performance, using this, we are able to get low latency applications as well, because the items get added in the queue in the same transaction. So it gets processed faster, and we don't need to wait for going out of band to any other system. And lastly, this is just showing our graphs these from one of our clusters that it's able to send to remote clusters, which are in East Coast, in a few seconds to replicate the metadata. And that's it. Thank you.
All right, I've got time for questions. Any questions?
Yeah, question about FoundationDB. Does it have, functions as a key value store, as I understand it. Does it have higher order functions like enabling leader election or locks? Are those things that you can implement on top? How do you implement those on top of it?
So it does have leader elections. So it does follow a philosophy of assigning the sequence to the commit. So the commits are serialized. So the protocol, it has its serializable consistency it provides. So that it has. For locking, what we typically do is we start the transaction, take a lock, and then basically commit it, and then every other worker that needs to see whether the lock is there, it will just basically check the row.
Okay.
But it doesn't provide any locking primitives out of the box. It's mainly provide transaction, and transactions have no boundaries. They are distributed. So they can be across
Got it. Okay.
shards,
So it's up to you if you want to build queues or other things like that, then you build on
Yes.
those mechanisms.
Queues. So we have built like queues, indexes, schemas, data
Yeah.
layout, and everything on top of it. But it provides some small low-level primitives using which you can build on top of it.
Thank you.
Do you know what algorithm it uses for the leader election under the hood?
So it has its own algorithm. So basically, it chooses one leader. The protocol itself is basically when the commit happens, the commit needs to be assigned a version. So for that, it chooses a sequencer, which is out of 5 coordinators. And it chooses a sequencer, and that sequencer is responsible for providing you the commit version. And that commit version is then used to commit or to order the commit. But it has its own protocol to choose sequencer. It doesn't use Raft or Paxos. Yeah.
Interesting. All right. Is that in one of the papers they released
Yeah.
around it?
Yeah.